many people here say, you know, when asked about jokes, say, oh, darn, I just heard a good one, I heard it, and you find out that you forget all the jokes you hear. And when it's your turn, you just can't remember. Isn't that true? Now, let me ask you a question. Which jokes is it that you remember? The ones you hear or the ones you tell? The ones you tell. If you want to be good at telling jokes, when you hear a good one, find a friend quick and tell it. Because once you've articulated it, once you've brought it up to the, to your verbal level, then it becomes like a part of you, and you can remember that, can't you? So that's why it's important when I say talk to your neighbor to really talk over the ideas, even if you already know them. Talk about the ideas. When you leave here, you go outside the classroom, talk about the ideas of physics with friends, okay? If you talk about those ideas, then they're going to become a part of you, and you'll find you remember them a lot more. You remember what you talked about, not what you heard about, you know? Okay, let's begin. What are we going to talk about today? We're going to talk about the idea of inertia. Inertia. Heavy anvil here has a lot of inertia. If this anvil started moving, maybe moving across the table, you would look for some kind of cause, wouldn't you? Or if this anvil started going up in the air, you would look for some reason for that. In these days, we know there are reasons for things. And whatever the reason might be, you would label it some kind of force. Because you know this anvil is not going to start going up in the air unless a force acts on it. Or it's not going to start sliding across the table unless a force acts on it. And so strongly embedded is the intuition that force is responsible to motion that years ago when the early Greeks were developing the ideas of science, Aristotle made that one of his dictums. And he said, hey, if things are moving that aren't supposed to be moving, well, we said the stars and the planets, those are supposed to be moving. But if things are moving that don't ordinarily move, you can be sure of one thing, gang, there's a force responsible. And that became like sort of a law of physics, that motion is associated with forces. No forces, no motion. Well, then about the time of Galileo, people were starting to question that because ideas came up like this. How about a cannonball? When a cannonball is fired from a cannon, it's easy to identify the force that gets that cannonball started, isn't it? It's the gunpowder exploding, isn't it? Doesn't no gas explode and push that ball right out the barrel, huh? That's easy enough. But the question was raised, hey, once it gets out there and the expanding gases no longer act on it, what keeps the cannonball moving? So strong was the idea that a force must be responsible that people started thinking about things like this. Well, when the cannonball moves through the air, it's going to part the air in front and leave a vacuum behind. Now, there was another little law. It says, nature abhors a vacuum. So there's not really going to be a vacuum tube left behind. That air that's been parted is going to squeeze back down and fill it up, isn't it? Now, you've taken a bath with ivory soap, okay? Floats, okay? Do you ever be in the bathtub and you start to grab the soap and what happens? It keeps going away from you? It was thought in the same way that the cannonball is being squeezed by the air behind, and it's the squeezing of the air that provides the force to keep it going. What do you think? A fellow by the name of Galileo turned the whole thing around. Read about Galileo's experiments with the inclined planes. I won't talk about that now. But the gist of it is this. Galileo discovered that once something is moving, which might require a force, but once it's moving, if there's no friction, that object is going to keep on moving anyway, with no reason, no force required. And that property of things to persist in their state of motion is what he called inertia. Doesn't say why, but it's just a property of things to do that. So if an object is moving, no force at all required to move it, if there's no forces acting on it. Now, if this is sliding across the table, you have to keep pushing it. That's because friction acts. But if I put this on the ice, where friction were very, very low, and I got it going, do I have to keep pushing it? Does a hockey player today, in seeing a puck come by, say, ooh, what's pushing that puck? No, we know that something got it started, but once moving, it will move of itself. Now, inertia, mass. What's mass? What's weight? What's inertia? All the same? Answer begins with an N. No. Okay? How about mass and inertia? Just about the same. We say mass is like the measure of inertia. Inertia is the tendency of an object to persist in its state. If it's moving, it's going to keep on moving. You get in outer space and take a ball and throw it. If there's no forces acting in the ball, it doesn't slow down to a stop. It just keeps going, 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 going. If you have an object out in space and it's at rest, you leave it alone. You come back centuries later, it's at rest, as long as no force acts. That's the idea of inertia. Okay, watch this gang. Inertia, huh? Card. Coin, huh? Yeah. A body at rest tends to stay at rest. I'll show you a nice one. Here's the one shown to me by my friend Marshall Allenstein. Okay. Get a little hoop like this. Balance something on the top like this. Marshall Allenstein. Good. Here's a block of wood. Does this block have any matter? Yeah, you can see it, okay? Have mass? To say it has mass is to say it has inertia. Right now it's at rest. Now what I'm going to do is I'm going to pull the tablecloth. I'm going to whip it. And when I pull that tablecloth, you're going to tell me, what do you suppose is going to happen to this block? One of three fates. Number one, recoils onto the floor. Number two, stays essentially where it is. Number three, follows along with me. Take a pick. Okay? Let's put it to experiment. And here we go. A 1, a 2, a 3. The staples provided the outside force that did move the block. But you know if there were no staples there, you know. If there's no staples, what? These are not staples. This is for real, okay? Okay? What do you mean, oh no? Do you believe in physics? Have I not shown you that physics never fails? Let's try this. And a 1, and a 2, and a 3. Okay. What do we got here? Iron ball. Iron ball got a lot of mass. Got a lot of mass? Got a lot of inertia. Turns out if something has a lot of mass, has a lot of inertia, it also has a lot of weight. And people get mixed up between how much mass something has and how much weight something has. That's because they're directly proportional. We measure the amount of matter in kilograms, kilos. We measure the amount of weight in pounds, or in metric system, in newtons, newtons of force. 1 newton is about equal to 1/4 of a pound, a little bit less than 1/4 of a pound. So most of the world use a newton as a unit of force. Here in America, we still use a pound. But pounds, newtons, synonymous. That's gravitational pull. How many kilograms is what? How much matter? It turns out this ball is kind of hard to shake back and forth, okay? A lot harder than, say, a feather. And if I get out into a region of the universe where all the gravities cancel out, gravity-free region, it's still going to be hard to shake back and forth because it still has the same amount of matter. It still has the same amount of inertia, but it might not have any weight. If you put this in a bathroom scale, no weight at all. Now I want to show you a demonstration which will demonstrate the property of weight and the property of inertia. Let's try it. What I'm going to do is I'm going to pull this lower string. And I'm going to pull it very slowly, harder, 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 until one of the string is going to break. What I want you to do with your neighbor is see if you can predict which of the two strings, the top or the lower, will be the one to break if I gradually pull it harder, 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 until snap-a-rooney. Talk it up. gang? How many say the top string's going to break because he's got the other string here ready for the next trial on the top? Good deduction. Let's try it. Watch this. It was the top. HC. Weight or inertia come into play. Weight. Very good. Let's look at this on the board. Okay. Now, I'm pulling down. I'm pulling with a force. Sets up a tension in there, doesn't it? In fact, I could go like that and it would sort of twang like a guitar string. Sets up a tension force, doesn't it, right? But isn't this tension force also transmitted up to the top string? If that's all the thinking we did, we would say, well, you have just as much tension in the lower string as the upper string. It's probably 50-50. Either one could break. Can you see there's something else to consider, though? Begins with a W, ends with a T. Weight. Okay, get that? This weight of this ball acts on which string? Only the top? Yes, only the top. So in addition to the tension that you're providing by pulling, you have the weight of the ball on this string. Now I think you can see there's more combined tension on the top than the bottom, and sure enough, the top one breaks. There's where weight comes into account. The force of gravity helps to make the tension in this one greater than in this one. Now I'm going to do it again. Only this time, I'm going to whip it down very quickly. I'm going to ask this ball to accelerate downward at a rate greater than free fall. I'm going to whip down with an acceleration more than 10 meters per second square. And I want you to predict which string is going to break. Check the neighbor right now. This is an easy one, isn't it? And what's it going to be, huh? Here we go. Bottom one. Okay? Now, what is at play here? Weight or inertia? Inertia. The tendency of this ball to remain at rest during that brief force doesn't let that tension get up here as readily, and so what happens? It happens down below. This ball is not going to whap go down faster than free fall. Instead, it's a little lazy. Lazy is another word for inertia in a sense. So the lazy ball stays there, and the bottom string breaks, and the top one, in a sense, is absorbed from the shock that otherwise would result. Can you kind of see that?